Hello everyone, and welcome to today's video lecture, which is on Stirling's formula, also known as Stirling's approximation. And this is a very famous result that was discovered jointly by the Scottish mathematician James Stirling and the French mathematician Abraham de Moivre, and they derived this result empirically. Today we're going to rigorously prove it. And our proof of Stirling's approximation is going to rely heavily on the Euler-Maclaurin summation formula. We've spent a lot of time in the last few videos on this channel developing the Euler-Maclaurin summation formula, and these videos culminated in my most recent video on the Euler-Maclaurin summation formula with the all-important remainder term. And so in today's video, what we're going to do is use the Euler-Maclaurin summation formula with remainder term to derive Stirling's formula. And Stirling's formula is an asymptotic formula. It describes the behavior of factorials as the factorial gets larger and larger and larger. And so what it says is that the limit as n approaches infinity of the expression n factorial, that gets asymptotically close to the formula n over e raised to the nth power times the square root of 2 pi n. So that's a very cool formula that involves both e and pi, and so we're going to unpack that a little bit now. So here's the motivating idea for the formula. We want a formula that characterizes n factorial as n grows larger and larger and larger. Well, n factorial just equals n times n minus 1 times n minus 2 times dot 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 all the way down to 3 times 2 times 1. N factorial is itself a product of n separate terms. And so if we want to think about the behavior of n factorial as n gets bigger and bigger, one thing that we might start by observing is that as n grows larger and larger, the terms in n factorial get proportionally closer and closer together, right? When n is small, when we have something like 3 factorial, which is 3 times 2 times 1, well, 2 is double 1, and 3 is 1.5 times 2. Those numbers are actually growing pretty fast. But when we have a large factorial, like a million factorial, well, 1 million proportionally isn't really a lot bigger than 999,999, right? It only differs by 1 millionth part. So to write that symbolically, as n grows very large, n is roughly equal to n minus 1 and roughly equal to n minus 2 and so on. And so in the limit as n goes to infinity, n factorial should be on the order of n times n times n, etc., dot, dot, dot. Well, that's n terms, so that's just n times itself n times, or n to the n. Now, of course, this is just a rough estimate for n factorial as n approaches infinity. We know that, in fact, that this is a overestimate because, by definition, in n factorial, every term in the product other than the leading term n is less than n. So clearly we're overestimating n factorial here. But as a rough guess, it's not bad. The question is just, can we do better? Well, it turns out that Stirling's formula actually provides an excellent estimate for n factorial, and as I've already mentioned, it is asymptotically equal to n factorial as n approaches infinity. So let's see how we get there. And here's our strategy. Instead of trying to evaluate the limit as n approaches infinity of the expression n factorial, let's consider instead the limit as n approaches infinity of the logarithm of n factorial. Now, why are we doing that? We're doing that because the logarithm of a product is equal to the sum of the logarithms of the individual terms in the product. And so by taking the logarithm, I'm able to utilize all the tools I have at my disposal to evaluate sums. And the particular tool I have in mind here, of course, is the Euler-Maclaurin summation formula. So explicitly what we're doing here is we're taking the log of n factorial, which equals the log of 1 times 2 times 3 times dot 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 times n minus 2 times n minus 1 times n close parenthesis, and then we're splitting that up into a sum of the logarithms of the individual terms in that product. So this equals the log of 1 plus the log of 2 plus the log of 3 plus dot 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 plus the log of n minus 2 plus the log of n minus 1 plus the log of n, which I can write more concisely as the sum from the index k equals 1 to n of log of k. So something really interesting is happening here. What we've found is by taking the logarithm of n factorial, we see that the log of n factorial is actually equal to the discrete summation of the logarithm function on the positive integers from 1 to n. And if you've watched my previous videos, you know that we can evaluate this sum, the sum of the values of log of k from k equals 1 to n, using the Euler-Maclaurin summation formula. So let's write down that formula now. I'm going to ask you to recall the following, which is that the summation of the values of some function f of k from k equals 1 to n, this is very general, this formula, equals the integral from 1 to n of f of x dx plus f of 1 plus f of n all over 2 plus the integral from 1 to n of the function fractional part of x, that's what x in squiggly brackets is there, minus 1/2 times f prime of x dx. This is the first derivative form of the Euler-Maclaurin summation formula with remainder, which I derived in my previous video. And I'll just remind you all that the expression inside the remainder integral, the polynomial fractional part of x minus 1/2, which is multiplying f prime of x, that expression fractional part of x minus 1/2 is just the first periodic Bernoulli polynomial. So that's the first derivative form of the Euler-Maclaurin summation formula in its most general form. And now if we want to apply it to our particular problem, we can plug in logarithm of x for f of x. And when we do that, we'll have that the log of n factorial equals the sum from k equals 1 to n of the logarithm of k, which equals the integral from 1 to n of log of x dx plus log of 1 plus log of n all over 2, plus the integral from 1 to n of fractional part of x minus 1/2 quantity times the derivative of the logarithm, which is 1 over x, dx. And it probably goes without saying here in this video that when I use the expression logarithm, I mean the natural logarithm, the logarithm with base e. Well, now we can start unpacking this formula a little bit. And perhaps the first thing to notice is that in the expression logarithm of 1 plus logarithm of n all over 2, well, the logarithm of 1 is just 0. So I can rewrite that term as just 1/2 times logarithm of n. And next we want to evaluate the definite integral from 1 to n of log of x dx. And so to do that, we need to use integration by parts. And so in this integration, I will let our variable u of x equal the logarithm of x, and I'll let the differential dv equal 1 times dx. So then we'll have u equals log of x, du dx equals 1 over x, so dx equals x times du. So 1 over x dx equals du. dv equals 1 dx, so integrating both sides, we have that v equals x. And so our integral is equal to v times u, the product v times u, that's x times log of x, evaluated at the endpoints 1 and n, minus the integral from 1 to n of v du. So the integral from 1 to n of v du here would be x times 1 over x dx, which just equals 1 dx. And now plugging in values, we get that this integral equals n times log of n minus 1 times log of 1 minus the integral from 1 to n of 1 dx. Well, the integral of 1 dx, of course, is just x. And so then when we evaluate that at the endpoints, that's going to be minus open parenthesis n minus 1. But then, of course, the log of 1 just equals 0, so that term cancels out. And we have that the integral equals n times the log of n minus n plus 1, applying the negative sign there. So we can plug that result into our formula here, and then in place of our integral from 1 to n of log of x dx, we have n times the log of n minus n plus 1. And so now the last piece of this equation that we need to consider is this funny looking integral over here, the integral from 1 to n of the fractional part of x minus 1/2, again that's the first periodic Bernoulli polynomial, times the derivative of log of x, which is 1 over x, dx. Now we're going to be considering what happens when we let n tend towards infinity. So figuring out what that integral equals is actually going to be a key part of this video. But I can't do that just by looking at it. I don't know of any really good ways to integrate this thing. It has a fractional part of x in it. It has a 1 over x in it. But separate to even evaluating this integral, I would like to try to answer the question of whether the improper integral, as n approaches infinity, whether that integral even converges. And to do that, I want to look at a slightly more sophisticated version of the Euler-Maclaurin summation formula, which is the second derivative form. And the second derivative form of the EMSF is a lot like the first derivative form. It contains a lot of the same elements. So we have by the second derivative form that the summation, the discrete summation of the values of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx. We have that also, of course, in the first derivative form of the formula, plus the correction term f of 1 plus f of n all over 2. And now in place of this error integral from the first derivative form, we have an additional correction term. We have plus 1/6 times f prime of n minus f prime of 1 all over 2. And then we have a new error or remainder integral minus 1/2 times the integral from 1 to n times the second periodic Bernoulli polynomial, which is fractional part of x squared minus fractional part of x plus 1/6 times f double prime of x dx. And if you're at all confused about where this formula comes from, please see my most recent video on the Euler-Maclaurin summation formula with remainder term, where I derive this and subsequent refinements of the EMSF with remainder. Anyway, now that we've written out the second derivative form of the EMSF with remainder, we can apply it to our logarithm function. So we'll have that the sum from k equals 1 to n of the natural log of k equals the integral from 1 to n of log of x dx plus the log of 1 plus the log of n all over 2 plus 1/6 times the derivative of log of x, which of course is 1 over x, so that'll be 1/6 times 1 over n minus 1 over 1 all over 2 minus 1/2 times the integral from 1 to n of the second periodic Bernoulli polynomial, I'm not going to read it out again, times f double prime of x dx, which here would equal negative 1 over x squared dx. Now we already know that the integral from 1 to n of log of n just equals n times the log of n minus n plus 1. And we also know that log of n plus log of 1 all over 2 just equals 1/2 of log of n, so I'll fill in those values there. And so the new information that we really gain from the second derivative form of the EMSF is that our error integral from the first derivative form, the integral from 1 to n of the first periodic Bernoulli polynomial times 1 over x dx, that integral must be equal to this new correction term, 1/6 times the quantity 1 over n minus 1 over 1 all over 2, and this new error integral. And because I have a negative 1/2 multiplying a negative quantity in the integrand, negative times negative, of course, is positive, so this will just be plus 1/2 times the integral from 1 to n of the second periodic Bernoulli polynomial times the function 1 over x squared dx. Now, as I said, what we're really interested in knowing is the behavior of these error integrals as n approaches infinity. And so I'm going to write limit as n approaches infinity on the left-hand and right-hand sides of this equation. And now, instead of n as the boundaries for our integral, I'll just write infinity there. And then if we just look at our correction term on the right-hand side, as n goes to infinity, that term 1 over n, of course, goes to 0. So this becomes a constant, and we just have 1/6 times negative 1 over 2, so that just becomes negative 1/12. Now, as I said, it's difficult to know whether the error integral from the first derivative form of the EMSF converges just by eyeballing it anyway. But on the right-hand side, we know that it's equal to this constant, negative 1/12, plus this other integral, 1/2 times the integral from 1 to infinity of the second periodic Bernoulli polynomial times 1 over x squared dx. And now we're actually in really good shape, because this second periodic Bernoulli polynomial is bounded. So let me show you very concretely why that's so. I'm going to graph here the second periodic Bernoulli polynomial, which is a function of the fractional part of x. So we have capital B2 of fractional part of x equals fractional part of x squared minus the fractional part of x plus 1/6. Well, the fractional part of x is just the non-integer part of x. You can think of it as x minus the floor of x. Well, from x equals 0 to x equals 1, x is just a fraction, so the fractional part of x just equals x. So our function, capital B2 of fractional part of x there, is just the parabola x squared minus x plus 1/6 evaluated on values of x from 0 to 1. At the endpoints of the interval x equals 0 and x equals 1, the fractional part of x, of course, just equals 0, so the function there equals 1/6. And now I hope it's clear why we call this a periodic function, because on all the other intervals, from x equals 1 to x equals 2, from x equals 0 to x equals -1, from x equals 2 to x equals 3, and so on, we're always evaluating x on the fractional part of x. The function essentially lops off the integer part of x and returns the same values for the function that we got when x was a fraction. And so we get repeating copies both to the left and to the right of the parabola evaluated from x equals 0 to x equals 1. Well, it turns out that the function hits its minimum when x equals 1/2, 1.5, 2.5, 3.5, and also -1/2, -2.5, -3.5, and so on. And there the function bottoms out at y equals -1/12. So we can see that the second periodic Bernoulli polynomial is bounded between 1/6 and -1/12. Or put another way, if I wanted to take the absolute value of this function, I would just reflect the negative parts of the function over the x-axis, and I would get a graph that looks like this. And now we can write that the absolute value of the second periodic Bernoulli polynomial is less than or equal to 1/6. So what do we get from that? Well, then we know that the right-hand side of this equation, which is -1/12 plus 1/2 times the integral, must be less than or equal to, again, -1/12, plus 1/2 times the integral from 1 to infinity of 1/6 times 1 over x squared dx. How do I know that? I know that because the integrand is the product of the second periodic Bernoulli polynomial and 1 over x squared, and I know by this bounding argument that we just gave that the absolute value of the second periodic Bernoulli polynomial must be less than or equal to 1/6, which means the entire integral must be less than or equal to 1/6 times 1 over x squared dx. Well, I can now pull that constant value 1/6 out of the integral, so I have that this expression on the right equals -1/12 plus 1/2 times 1/6, which is 1/12, times the integral from 1 to infinity of 1 over x squared dx, and the integral of 1 over x squared dx from 1 to infinity converges. So I know that if the right-hand side of the equation is bounded by a finite quantity, the constant -1/12 plus 1/12 times the integral from 1 to infinity of 1 over x squared dx, then I know that the left-hand side of the equation, which is just this integral, fractional part of x minus 1/2 times 1 over x dx, evaluated from 1 to infinity, I know that that integral must also converge. So putting it all together, we have that the log of n factorial equals the sum from k equals 1 to n of the log of n, which equals n times the log of n minus n plus 1, plus 1/2 times the log of n, plus this integral, the integral from 1 to n of fractional part of x minus 1/2 times 1 over x dx. And just rearranging a little bit, I'm going to move the plus 1 down to the second line there. And taking the limit as n approaches infinity, we then have that the limit as n approaches infinity of log of n factorial equals the infinite sum from k equals 1 to infinity of log n, which equals the limit as n approaches infinity of n log n minus n plus 1/2 log n plus 1 plus the integral from 1 to infinity of the first periodic Bernoulli polynomial times 1 over x dx. And we've shown that that integral must converge. I don't yet know what that integral converges to, but I know that in the limit as n approaches infinity, it's converging towards some constant. So if we look at this formula, we have a bunch of terms in n, and then we have the constant 1 plus this integral, which is also converging towards some constant. Let's just combine these finite quantities together and group them under the term c of n, the constant whose value is ultimately determined by n. And now our goal is going to be to determine what that constant c of n should be as n approaches infinity. Now, I believe historically, Stirling found C of n empirically. He didn't have the Euler-Maclaurin summation formula at his disposal, but we do, and we're going to use it here. So here it is now. The log of n factorial equals n log n minus n plus 1/2 times the log of n plus our function c of n, where again c of n equals 1 plus the integral from 1 to n of the first periodic Bernoulli polynomial times 1 over x dx. Now, if we played around with this formula and tried it out on different products, we might eventually turn to double factorials. Double factorials are like factorials, but you skip every other number. So, for example, 2n double factorial would be 2 times 4 times 6 times 8 all the way up to 2n. So if I want to consider the logarithm of 2n double factorial, that's log of 2 times 4 times 6 times 8 all the way up to times 2n, well, the first thing I might realize is that I can factor out a 2 from each of those terms. I have n such terms with 2 as a factor, so this logarithm would actually equal the log of the quantity 2 to the n times 1 times 2 times 3 times 4 times all the way up to n. In other words, 2 to the n times n factorial. By the rules of logarithms, this is going to equal the log of 2 to the n plus the log of 1 times 2 times 3 times all the way up to n. And then again, by the rules of logarithms, this is going to equal n times the log of 2 plus the log of n factorial. And then applying the EMSF to this expression, we have that the log of 2n double factorial equals n times the log of 2 plus, and now just the EMSF, n log n minus n plus 1/2 log n plus c of n. Now let's consider what the result would be if I took the logarithm instead of 2 times 4 times 6 times times 2n. What if I took the log of 2 times 2 times 4 times 4 times 6 times all the way up to 2n times 2n? Well, that's really the log of 2 squared times 4 squared times 6 squared times all the way up to 2n squared. In other words, it's really just the logarithm of 2n double factorial squared. By the rules of logarithms, I can pull down that exponent in front as a coefficient. It will equal 2 times the log of 2 times 4 times 6 times 8 times up to 2n. And we already found what that expression equals. So this new expression, the log of 2n double factorial squared, that'll just equal 2 times n log 2 plus 2 times n log n minus 2n plus 2 times 1/2 is plus 1 times log of n plus 2 times c of n. Now I just want to simplify this expression a little bit. I have the term 2n log n and I have the term log n. I can combine those together to make 2n plus 1 log n. So let me just group those terms there. But now I have a 2n log 2 plus a 2n plus 1 log n minus 2n plus 2 times c of n. I'd like to get this even simpler. So what I'm going to do is I'm going to add a creative form of 0 to this expression. I'm going to both add and subtract log 2. So when I do that, I'll have 2n log 2 plus log 2 minus log 2, that's the creative form of 0, plus 2n plus 1 log n minus 2n plus 2 times c of n. And now I can combine 2n log 2 with log 2 together to make 2n plus 1 log 2 plus 2n plus 1 log n. I hope you see how that's nicer. Minus log 2 minus 2n plus 2 times c of n. And now I can simplify even further. This will equal 2n plus 1 times the quantity log of 2 plus log of n minus log 2 minus 2n plus 2 times c of n. So this will then equal 2n plus 1 times log of 2n minus log of 2 minus 2n plus 2 times c of n. And let me just put a box around that identity. So that's the first identity that we'll need. We'll also need the following identity. We have, again by the EMSF, that the log of the factorial of an odd number, in other words, the log of 2n plus 1 factorial, equals, by the EMSF, 2n plus 1 log of 2n plus 1 minus the quantity 2n plus 1 plus 1/2 times the log of 2n plus 1 plus 1 plus the integral from 1 to 2n plus 1 of the first periodic Bernoulli polynomial times 1 over x dx. Now, I'll just group those last two terms together and call them c of 2n plus 1. So I just want to rewrite that formula here, and I'm going to put a box around this equation. This is the second identity that we're going to need for the derivation. And so now what we're going to do is subtract the second identity, the second equation, from the first identity, the first equation, and take the limit as n approaches infinity to determine c of n. So on the left-hand side, we're going to have the log of 2 times 2 times 4 times 4 times 6 times 6 times ... all the way up to 2n times 2n, minus the log of 1 times 2 times 3 times 4 times 5 times 6, all the way up to 2n plus 1. And then on the right-hand side, we're going to have all that stuff in the first equation minus all that stuff in the second equation. And now we can immediately rewrite the left-hand side of this equation, recalling from the rules of logarithms that the difference of two logarithms is equal to the logarithm of the quotients of the terms. So the left-hand side of the equation will become the log of 2 times 2 times 4 times 4 times 6 times 6 times ... all the way up to 2n times 2n over 1 times 2 times 3 times 4 times 5 times 6 all the way up to 2n plus 1. And then on the right-hand side, I have the difference of all these terms. I'll try to group them together in a way that makes sense. We'll have 2n plus 1 times log of 2n minus 2n plus 1 times log of 2n plus 1 minus the log of 2 minus 2n, and then we have a double negative here, so plus 2n plus 1, then minus 1/2 log of 2n plus 1 plus 2 times c of n minus c of 2n plus 1. The first two terms can be grouped together by the laws of logarithms. These become 2n plus 1 times the log of 2n over 2n plus 1. And then, of course, the minus 2n and the plus 2n cancel out, and the other terms are unchanged so far. Now I want to get rid of that minus 1/2 times log of 2n plus 1 term, so I'm going to add it to both sides of the equation. And now that that term, 1/2 times the log of 2n plus 1, is on the left-hand side of the equation, I can rewrite that as log of 2n plus 1 to the 1/2 power. And then by the rules of logarithms, I can pull it into the product of terms, and so it's going to show up there as the final term in the numerator, 2n plus 1 to the 1/2. Now, if we look at this quotient, we see a lot of redundant terms. So it's time to do some cancellations here. I'm going to cancel a 2 from the numerator and the denominator, a 4, a 6, all the way up to 2n, and then for that very last term I have 2n plus 1 to the 1/2 over 2n plus 1. I can cancel the 2n plus 1 to the 1/2 in the numerator and rewrite the denominator term as the square root of 2n plus 1. So cleaned up, our left-hand side of the equation is the logarithm of 2 times 4 times 6 times 8 times ... times 2n minus 2 times 2n all over 1 times 3 times 5 times 7 times ... times 2n minus 1 times the square root of 2n plus 1. And we have one final adjustment to make on the right-hand side of this equation here. I'm going to rewrite that first term, 2n plus 1 times the log of 2n over 2n plus 1. I'm going to rewrite that term in the logarithm by taking the reciprocal. So I'm going to rewrite it as the log of 2n plus 1 over 2n raised to the power of negative 1. And that just simplifies to 2n plus 1 times the log of 1 plus 1 over 2n to the negative 1. And now that I've done that, it might seem reasonable to actually break up this term, so I'll do that. So this term is going to equal 2n times the log of 1 plus 1 over 2n raised to the negative 1, plus 1 times the log of 1 plus 1 over 2n raised to the negative 1. And then all the other terms remain, minus log 2 plus 1 plus 2 times c of n minus c of 2n plus 1. And now we're finally ready to take the limit as n approaches infinity. So doing that, taking the limit as n goes to infinity on both sides of the equation, look what happens to our expressions c of n and c of 2n plus 1. Recall that c of n is a constant whose value depends on n, and it equals 1 plus the integral from 1 to n of the first periodic Bernoulli polynomial times 1 over x dx. And by the same token, c of 2n plus 1 is a constant that depends on the value 2n plus 1, and it equals 1 plus the integral from 1 to 2n plus 1 of the first periodic Bernoulli polynomial times 1 over x dx. Now we've already seen as the upper bound of integration on this integral goes to infinity, the interval converges. And now the key insight is to realize that as n goes to infinity, these integrals in the limit are equal. Whether I make the upper bound of integration n or 2n plus 1, once I let n go to infinity, in the limit these integrals represent the same quantity. Therefore, as n approaches infinity, c of n equals c of 2n plus 1. So in this equation now, I can replace c of 2n plus 1 with just c of n. So I have 2 times c of n minus c of n, which of course just equals c of n. Another very notable thing happens as I take the limit as n goes to infinity. In that first term, where I had 2n times the log of 1 plus 1 over 2n to the negative 1, I can rewrite that term as the log of 1 plus 1 over 2n to the negative 2n, and then something awesome happens. That term becomes the log of e to the negative 1. That just comes from the definition of e. And so the natural log of e to the negative 1 is just negative 1. And so now on the right-hand side of the equation, I have a negative 1 and a positive 1. Those terms cancel. And then turning our attention to the other term, minus 1 times the log of 1 plus 1 over 2n. As n goes to infinity, that becomes minus 1 times the log of 1. The log of 1 is just 0, so that term also cancels out. So this is pretty amazing now. All I'm left with on the right-hand side is the limit as n approaches infinity of negative log of 2 plus c of n. Well, let's simplify that by just adding log 2 to both sides of this equation. And now we're finally in a position to solve for c of n as n goes to infinity. And in order to do that, we need to recall the Wallace product. The Wallace product is this amazing infinite product, and I actually derive it for you guys in my video on the infinite product formula for the sine function, which you can find on this channel if you're not familiar with this already. Anyway, the Wallace product says that the limit as n approaches infinity of the quotient 2 times 2 times 4 times 4 times 6 times 6 times 8 times 8 times 2n minus 2 times 2n minus 2 times 2n all over 1 times 3 times 3 times 5 times 5 times 7 times 7 times 9 times times 2n minus 3 times 2n minus 1 times 2n minus 1 times 2n plus 1, that this infinite product, really the quotient of these two infinite products, equals pi over 2. And now what we're going to do is take the square root on both sides for the Wallace product. And by taking the square root on the left-hand side, all of these duplicated terms cancel out in the numerator and in the denominator. In fact, by taking the square root, the only term that remains that still has a square root in it is that last term in the denominator, the 2n plus 1, because it's not duplicated. So once we clean this up a little bit, we have the limit as n approaches infinity of 2 times 4 times 6 times 8 times times 2n minus 2 times 2n all over 1 times 3 times 5 times 7 times 9 times all the way up to 2n minus 1 times the square root of 2n plus 1 equals the square root of pi over 2. And that infinite product is exactly what we have in the top line inside the logarithm. So therefore we have that the log of the square root of pi over 2 plus the log of 2 equals the limit as n approaches infinity of c of n. So now by the rules of logarithms, I can combine those two terms together, and I have log of 2 times the square root of pi over 2 equals the log of, I'm going to now bring that 2 inside the radical, the log of 2 squared times pi over 2. And now the exponent is canceled by the term 2 in the denominator there. So we have the log of the square root of 2 pi equals the limit as n approaches infinity of c of n. So I'm going to put a box around that result and bring it to the right side of the screen there at the top. And now we're ready to put everything together, because recall, by the EMSF, we have that the logarithm of n factorial equals n times the log of n minus n plus 1/2 times the log of n plus our remainder c of n. And now taking the limit as n approaches infinity on both sides, we have limit as n approaches infinity of the log of n factorial equals the limit as n approaches infinity of n log n minus n plus 1/2 log n plus the log of the square root of 2 pi. And now finally, exponentiating both sides, we have that the limit as n approaches infinity of e to the log of n factorial equals the limit as n approaches infinity of e to the n log n minus n plus 1/2 log n plus log radical 2 pi. Well, the left-hand side just simplifies to limit as n approaches infinity of n factorial, and the right-hand side I think is more convenient to write as a product of terms. I'm going to rewrite that as e to the log n to the n times e to the negative n times e to the log of n to the 1/2 times e to the log of radical 2 pi. Then we'll have the limit as n approaches infinity of n factorial equals n to the n times 1 over e to the n times n to the 1/2 times radical 2 pi. And now combining terms, this will equal n over e to the n times radical 2 pi n. And we've done it. We've derived Stirling's formula. So let me put a box around this. This is our final result, that the limit as n approaches infinity of n factorial equals n over e to the n times radical 2 pi n. And I just want to remark that apart from the fact that this formula is so beautiful and concise and contains the all-important constants e and pi, it also converges very quickly. So you can try this for yourselves at home. Try plugging some small numbers into Stirling's formula, and you'll see just how well it approximates the factorial, even with small integers like 5 or 6. And of course, the formula asserts that as we choose larger and larger integers, that approximation gets better and better and better. Stirling's formula, of course, also makes the computation of factorials so much easier, especially for large factorials. If you were writing a computer program and you wanted to compute, say, 1,000 factorial, instead of having the computer carry out 1,000 multiplications, 1,000 times 999 times 998, and so on, you could just have the computer use Stirling's formula and very accurately estimate 1,000 factorial with just a handful of calculations. Well, that's it for today. Thank you for watching, and if you enjoyed this video, please like or subscribe to my channel. Thanks again.